Start the session. So the next talk is by Professor Dmitry Talalaev. He's from Moscow State University, and he's going to talk about alternative algebraic structures in low-dimensional topology. So over to you, Dmitry.
Okay, thank you very much. I'd like to start with a few words in Russian in the occasion of the anniversary. В общем, я присоединяюсь ко всем поздравлениям, которых, наверное, уже было очень много сказано. Восхищаюсь, уважаю обоих этих людей, не знаю, кого больше, Андрея Юрьевича за создание изумительной, плодотворной среды вокруг себя. Конечно же, это является следствием богатых внутренних человеческих качеств. Валерий Георгиевич меня поражает как соавтор, как математик с неутомимым и неутолимым творческим движением вперед. Тоже не знаю, с чем такое замечательное свойство можно сравнить. Вот теперь я перехожу к теме моего доклада. I'm sorry, now it's...
Спасибо, Дима, спасибо за добрые слова, очень приятно.
So alternative algebraic structures and low-dimensional topology. Maybe it's better to say different algebraic structures. My talk is related with such keywords in topology, in mathematical physics, and algebra. And some of the material of my talk is based on joint works with Valeriy Georgievich Bardakov. Let me start with very general ideas. So one of the principal tasks in low-dimensional topology is the problem of finding invariance of such structures as knots, two knots, links, three manifolds. And the algebraic structures related to these problems are twofold. The principal algebraic structure. One of them is a fundamental group or a fundamental quandle of a complement of a knot. And another is the break group and the presentation of a knot in terms of the break group. From the first point, from the first observation, these structures are different. The fundamental group of a knot appeals to the structure of a quandle. To the quandle, its characters and representations. On the other hand, the break group realization triggered to the theory of the Yang-Baxter equation and the quantum group theory. These approaches look competitive, but I hope there is a unifying technique related to the bialgebra deformations, analogous to the Lie bialgebra deformations. I'd like to start with the basic definitions. A RAC is an algebraic structure, so it's a set with the binary operation, star with the following properties. So the invertibility, the first property is invertibility of the multiplication, and the second property is the self-distributivity of this operation. And with additional condition, with idempotence of this operation, this RAC is called a quandle. And there are very important examples of quandles. And the first one is provided by group structure. So if G is just a group, we can define conjugacy operation defined by this formula. And with this operation, this G is a quandle. Another quandle is known as an Alexander quandle, and it is given by this operation. It plays an important role in the invariance theory of knots. Despite the basic examples of quandles comes from the group structure, this structure is quite richer. So, for example, on the set of three elements, there are three different non-isomorphic quandle structures. expressed in these tables, the multiplication tables for such quandles. The trivial quandle, the quandle of the diedral quandle, and the third one. So, principally, the quandle appears in knot theory due to the following construction. Let D be a diagram of a knot. We can construct such an algebraic structure. We associate generators of a quandle with edges with arcs of a diagram, and at each crossing point of a diagram, we suppose the Wirtinger relations. It could be showed that this object is a quandle, and that equivalent diagrams produces isomorphic quandles. One could define a cohomology theory of quandles in full analogy with cohomologies of groups. So it is defined on the complex CRN of X, which consists of linear combinations of formal linear combination of n tuples of elements of X with the differential, which is expressed by this formula, and with some ramification, considering the quotient with respect to this complex of diagonals, so of such tuples with coinciding neighbor terms in n tuples of elements of X. And then we define the homologies and cohomologies of quandles with coefficients in groups in group G by calculating the differentials of such forms. And the important theorem of Carter, Kamada, and Saeta make a relation between cohomologies of quandles and invariants of knots. So let us consider a quandle X, an abelian group G, an element phi, which is a Tuka cycle of a quandle X with coefficient in G. Let D be a diagram of a knot K with a coloring rho, which is just a homomorphism from the fundamental quandle of X. Fundamental quandle of K in X. And then the partition function defined by a diagram is a sum over all such colorings of all such homomorphisms of the product over the points of the crossing points of a diagram. And in each point we find the value of a Tuka cycle on two colors of attaching arcs of a diagram, and S is the sign of this crossing point. So the theorem states that this partition function is an invariant of a knot. So there is one step in analyzing the Rex structure, the quandle structure. It is a Rex bialgebra structure. So let A be a linear space with linear multiplication and co-multiplication, and additionally we suppose that co-multiplication is co-associative. And the consistency relation between multiplication and co-multiplication is expressed by this formula. Here I use the Swidler notation for the co-multiplication. The simple example is such is defined by a quandle. So let G be a finite quandle, and K of G is just the linear space generated by element of quandle G. And the multiplication and co-multiplication on this linear space are defined as linear extension of operations on basis elements. And this is defined by this formula. So multiplication is of basis element is just the element corresponding to the multiplication of elements of a quandle, and co-multiplication is just group-like on basis elements. So if we extend such operation on all this linear space, we obtain a reg by algebra. Another important example of reg by algebras comes from Hopf algebras. So let H with additional with all its structures is a Hopf algebra, and the space, and then we consider new multiplication operation on the space H, which is given by this formula. So it's an analog of the conjugation in Hopf algebras with respect to the antipode element S. So the statement is the same. So this structure provides an example of reg by algebras. As I explained at the beginning of my talk, there are two sides of algebraic problem of finding invariance. One is related with quandles and another with braid group or Yang-Baxter equation. So I need to say something about the Yang-Baxter equation. It is a very known equation, so it is expressed by this formula. The set with such map R, I will call the Yang-Baxter set, and its braid analog is a set with a map which solves the braid equation. And these notions are related in a very strong and simple way. So if P is just a transposition of arguments, then the composition of S with P is a solution of the Yang-Baxter equation, and vice versa. And such a set I will call the braided set. There is a very known relation between self-distributivity property and the braid equation. So let star is a self-distributive operation, like in regs and quandles. Then the following map with two arguments and with two issues. But y is the same y as the argument, but the second argument, the second result is just the application of the self-distributive operation. So a very known proposition says that this map defines a braided set structure on X if and only if star operation is self-distributive. So it's a way to compare the Yang-Baxter structure or braid group structure with the quandle structure. So there is such relation, but you see it relates the such structure, the structure of braided set of the very particular form. So to illustrate better the role of the Yang-Baxter equation in the theory of knot invariance, it's better to go to the category of tangles. So it is also the very known construction. So the tangles are borders between sets of oriented points, and the category of tangles can be realized by such a set of morphisms. So they are expressed by such diagrams, and their relations are listed here. one more definition. So the Riemann-Hopf algebra is a Hopf algebra with additional element U and V, which satisfies such additional properties. It is not so it is important very generally in my talk. So the important example of such Riemann-Hopf algebra is the universal enveloping algebra of SL2. And the additional structures here are the R matrix, the universal R matrix, which is given by such an expression, and with the special element V, which is just the exponential of the Cartan element in this universal enveloping algebra. So the theorem, which is very general, the theorem constructing the Reshetikhin-Turaev invariance of knots says the following, that we can define a functor from the category of oriented tangles to vector spaces in such a way that the ordered set of points is mapped to the tensor product of some vector spaces, and the morphisms are mapped to morphisms to linear operators in this category, and these linear operators are constructed with the help of the representation of R matrix. So in this case, the representations of the universal R matrix, but in general, they are constructed by solution of the Yang-Baxter equations. Yang-Baxter equation. Here they use this additional element V, and the okay, so it's a functor from the category of oriented tangles to vector space, but the most important in the theory of knot invariance is that this functor is isotopy invariant. So it produces invariant of links. And in the case of the universal enveloping algebra of SL2, it coincides with the Jones polynomial of links. So this theorem illustrates the importance of Yang-Baxter equation in knot theory, and the natural problem very close to the problem of integrable systems, discrete integrable systems, is the problem of finding solution of the Yang-Baxter equation, or in other words, finding a way to construct a new solution from the known solution for the Yang-Baxter equation. And in this context, I would like to provide some result obtained in collaboration with Valeriy Georgievich Bardakov. So let A be a Hopf algebra. It is called almost cocommutative if there is an invertible element R in its tensor square, such that commultiplication in opposite order is just a conjugation of the normal commultiplication of an element A by this element R. If one has two such Hopf algebras over a commutative ring K, one can construct its tensor product. So here is its definition, which is also a Hopf algebra. And the operation on this tensor product are given by this formula. So it's just the conjugation of commultiplication. The multiplication is just the multiplication of tensor product of two algebras, and commultiplication is given by the tensor product, but conjugated by this element R, which solve additional equations. Here is the formula for the antipode in this Hopf algebra, co-unit.
Does your R satisfy the quantum equation here?
Yes. But this one, it is not the Yang-Baxter equation.
Okay.
You see, R is an element of C cross B. Delta C is application of commultiplication in C, and it should satisfy such equation.
I see.
Okay. Yes, it is necessary for properties of this Hopf algebra. Okay. So our theorem says that under the condition of the previous construction, so principally these are these equations. If additionally B and C are quasi-triangular, so they come with a solution of the Yang-Baxter equation, or more precisely with solution of the quasi-triangularity equation like this, then B tensor product with C is also a quasi-triangular Hopf algebra with structure element are beautiful, given by this formula, and it solves the Yang-Baxter equation in the tensor product of B and C. Just a remark that in a simple example, then B coincided with C, this construction produces such a solution for the Yang-Baxter equation. So if we have a solution of the Yang-Baxter equation, we can apply such formula to produce a solution on the tensor square of the same space. And this formula is different from the very known construction, which is called the fusion R matrix in tensor product. So it's a way to produce new solution from the known ones. Okay, the next part of my talk is about the relation between two such approaches. So you remember that starting from a quandle, from the fundamental quandle, and considering its homomorphisms to other quandles or characters or representations, one can produce the partition functions of Carter, Kamada, and Saeta, and it produces invariants. If one has a realization of a knot in terms of the braid group or in terms of tangles, one can represent morphisms in such category or elements in the braid group as solutions of the Yang-Baxter equation, and also considering some representations of such structures, considering characters of some structure, we can produce invariants of knots. Okay. There is another way of thinking about two disconstructions. It is also very known. So let I remember this construction. So let sigma be a solution of the braid relation. I will call the parts of this map like here, and let this map be left non-degenerate. It means that this map from X to the right part of this two-folded map is a bijection for all values of y. And we denote it in inverse with the fixed y by r y minus 1. So it means that the following fulfills. Let us introduce new operation. X point y is the left part of this braiding. There, the argument is an inverse of Ry of x. So like this. It could be illustrated by this scheme. So normally braiding is the arrow which comes from down to up direction, and it produces two components of this braiding starting from x and y. Do you see my mouse?
Yes, we can see.
Okay, thank you. Okay, and the left non-degeneracy of sigma means that we can change the direction in this diagram. So we can start from argument x and y and calculate values on the left side of this diagram. So, and this operation x point y is just this this value. Okay. Proposition by Victor Lebetin and Leandro Vendramin. Let sigma be a left non-degenerate braiding, then such an operation is a self-distributive operation. So we can construct a multiplication in some self-distributive structure starting from every braiding. They construct a family of maps which goes from Cartesian powers of the set X to itself, which are defined by this formula. So they apply the right part of the braiding map subsequently to each components of this entuple. And the statement says that these braidings, the initial sigma and the braiding sigma prime, which is given by this operations, but this operation is a braiding due to the known theory. So this says that two such braiding are conjugated by the guitar map, which is given here, but they are conjugated as maps in the Cartesian power of X. These braiding are not isomorphic in the sense of the braided sets. So they are not, they could not be conjugated sitting in X cross S, X cross X, but extending this set, we can conjugate one to another by this family of guitar maps. And from our topological problem, it means, okay, let I repeat the topological question. So the natural way to construct invariants of links, quantum invariants, is to use the realization of a link in the braid group and then calculate characters in some representation of Bn. Theorem of Lebetin and Andrei shows that this class of invariants can be passed through representation of a self-distributive structures. So principally it means that topological invariants obtained in two such approaches coincide. And the last sentence is about some future project which is related with the hope to find generalized approach unifying two of such approaches, and okay, and I hope that there is some way to to find the unifying approach related to the rec bialgebras and its representation. Okay, I think it's better to stop here. I plan to speak a little bit the next step generalization, means generalization in the theory of two knots. Okay, but my principal goal is fulfilled. Thank you very much.
Thank you, Professor Talalaev. Are there any questions or comments?
Can I ask?
Yes, please.
Yeah, so, Dima, please, can you tell something about this kind of Lebedev invariance for nodes or links? Is just some idea, or there are some concrete examples?
I suppose they construct something. Well, but in my talk, the principal point was that this guitar map unifies the approaches, you see.
Okay. Thank you.
Andrei, I think that we did not construct node invariant because for them more interesting some algebraic structures. For example, solution for the Young-Baxter equation. You know what Vendramin introduced braces and so on. We are not specialists in node theories. And also, can I ask Dima, and maybe it will be interesting for Mahender, the next question, we discuss it with Igor Nikonov from the Moscow. The question is the following. We know the definition of homologies for Quandl. Now we are going from Quandl to Quandl algebra. Is it true that with homologies we can introduce for the Quandl algebras? Is it some construction automatically we can describe this, or it's need to introduce some more definition, blah blah blah, or we don't have nothing new from the theory of homologies of quantums? What do you think?
I think that we discussed something in this direction, and that in fact, it's another question. So I think that the cohomology of Quandls describe the deformations of rec algebras.
You think that it's need to consider the deformations? But maybe this functor is linear, and maybe we cannot find anything new in homologies for Quandl algebras. Or we can construct some new homologies. What do you think?
I could not say. So for me, it's a very rich structure, and it should be extended, should be explored.
Okay, thank you. And now maybe next some philosophical questions. We know that for not Quandl is a very good invariant. In some sense, it's full invariant. And Carter Kamada used 2 cocycle for definition of not invariant. But is it possible to use 3 cocycles, 4 cocycles, and so on to define some type of invariance? What do you think?
I know that the 3 cocycle are used to find the invariance of 2 knots.
2 knots. And the classical knot, is it possible to use?
I'm not sure that it is natural.
No, but what does mean natural, Dima? See, have a look. If we have a Quandl, not Quandl, then it's invariant. And now we construct something from this invariant. 2 cocycles, 3 cocycles, blah, blah, blah. But why we cannot use these elements for definition of not invariance?
I don't know how, because 3 cocycle has 3 arguments.
Actually, Valeriy, so can I comment something? So The two co-cycle they use because the co-cycle condition arises just from the third Reidemeister move. So that is the principal reason for using two co-cycle. So if you try to use three co-cycle, then you have to either take into consideration regions or do some other stuff. So the two co-cycle condition is exactly the Reidemeister theorem, Reidemeister move, third Reidemeister move.
So it's natural to use the three co-cycle condition in Rosman move in theory of two nodes.
Surface node, yeah.
Because there are free arguments, free incoming two faces.
Yes, yes.
Yes, because it connects with the Young-Baxter equations. In fact, Young-Baxter equation, we have two arguments, and we can consider two cocycles.
Absolutely.
Yes. Thank you. Very good.
Thank you very much. Any more questions, comments?
Maybe last question. Excuse me. Definition of when Dima give free non-isomorphic free elements quantals, he used the notation T3 is trivial free element quantals. After this R3, it's diedral quantal, and the last quantal CZ4. Do you know what is the strange notation?
No.
Mahen, maybe you know. It's in fact a Jones quantal. It's very popular.
Yeah, it is the third quantal. It is the third quantal in Joyce list.
Yes.
Yeah.
But what is the strange notation? Do you know?
I don't know. Perhaps he had some motivation, but I did not find it in his paper. We wondered about it some time back.
Okay. Thank you.
Thank you. Okay, so if there are no more questions, let us thank Professor Dmitry Talalaev once more for the nice talk.
Thank you.
So,